Welcome to the chapter on fluid mechanics. Fluid mechanics is a branch of physics that deals with the mechanics of fluids and the forces acting on them. In this chapter, we will cover the fundamental properties of fluids, the principles of fluid statics, and the basics of fluid dynamics. Understanding the properties of fluids is fundamental to fluid mechanics. Key properties include density, viscosity, surface tension, and compressibility. Density, represented by the symbol ρ, is the mass per unit volume of a fluid. It is given by the formula ρ equals m divided by v, where m is the mass and v is the volume. The SI unit of density is kilograms per cubic meter. Viscosity, represented by the symbol μ, is a measure of a fluid's resistance to deformation or flow. It describes the internal friction of a moving fluid. The SI unit of viscosity is the Pascal second. Surface tension, represented by the symbol sigma, is the elastic tendency of a fluid surface which makes it acquire the least surface area possible. It is responsible for the shape of liquid droplets. The SI unit of surface tension is newtons per meter. Compressibility, represented by the symbol beta, is a measure of the relative volume change of a fluid as a response to a pressure change. It is defined by the formula beta equals -1 over v times the partial derivative of v with respect to p, where v is volume and p is pressure. Fluid statics, or hydrostatics, is the study of fluids at rest. It deals with the forces and conditions in a fluid that is not in motion. Pressure, represented by the symbol P, is the force exerted per unit area. It is given by the formula P equals F divided by A, where F is the force and A is the area. The SI unit of pressure is the Pascal. In a fluid at rest, the pressure at a point within the fluid is called hydrostatic pressure. It increases with depth due to the weight of the fluid above. The hydrostatic pressure at a depth h in a fluid of density ρ is given by the formula P equals P sub 0 plus ρ gh, where P sub 0 is the pressure at the surface, g is the acceleration due to gravity, and h is the depth. Pascal's law states that a change in pressure applied to an enclosed fluid is transmitted undiminished to all portions of the fluid and to the walls of its container. This principle is used in hydraulic systems. Buoyancy is the upward force exerted by a fluid on a submerged or partially submerged object. According to Archimedes' principle, the buoyant force is equal to the weight of the fluid displaced by the object. The formula is F sub b equals ρ vg, where F sub b is the buoyant force, ρ is the fluid density, v is the volume of the displaced fluid, and g is the acceleration due to gravity. Fluid dynamics is the study of fluids in motion. It involves the analysis of the forces and energy transformations in flowing fluids. The continuity equation is based on the principle of conservation of mass. For an incompressible fluid, it states that the mass flow rate must remain constant from one cross-section of a pipe to another. Mathematically, it is expressed as A1 V1 equals A2 V2, where A1 and A2 are the cross-sectional areas at points 1 and 2, and V1 and V2 are the fluid velocities at these points. Bernoulli's equation relates the pressure, velocity, and elevation in a moving fluid. It is derived from the principle of conservation of energy and is given by the formula P plus 1/2 ρ v squared plus ρ g h equals a constant, where P is the pressure, ρ is the fluid density, v is the fluid velocity, g is the acceleration due to gravity, and h is the elevation. The shape of an airplane wing is designed to create a difference in velocity between the air flowing over the top and the bottom of the wing. According to Bernoulli's principle, the pressure on the top surface is lower than the pressure on the bottom surface, creating lift and allowing the airplane to fly. Viscous flow refers to fluid motion that is significantly affected by viscosity. The Reynolds number, represented by the symbol Re, is a dimensionless quantity used to predict flow patterns in different fluid flow situations. It is defined by the formula Re equals ρ VL divided by mu, where ρ is the fluid density, v is the fluid velocity, L is a characteristic length, and mu is the fluid viscosity. For Re less than 2000, the flow is generally laminar. For Re greater than 4000, the flow is generally turbulent. For RE between 2000 and 4000, the flow is in the transition region. This concludes our chapter on fluid mechanics. We have covered the fundamental properties of fluids, the principles of fluid statics, and the basics of fluid dynamics. Understanding these concepts is crucial for solving real-world engineering problems involving fluid flow and behavior.